if you break your arm, an X-ray gives you a pretty binary answer, right? Broken or not.
Yeah, exactly. The doctor just points to that jagged white line on the screen, and that's it. It's clean. It's undeniable.
Right. But when you try to feed your company's proprietary IT manuals into a large language model, that diagnostic machine just, it absolutely shatters.
Oh, completely.
Yeah.
We treat AI like it's magic. You type a question, and it effortlessly gives you an answer.
Yeah, but today we're ripping up the floorboards to look at the frantic, messy plumbing underneath all of that. You sent us this massive stack of architecture diagrams, GitLab workflows, database documentation.
Because you're trying to build a retrieval pipeline for your internal IT team, and you are just hitting a massive wall.
Yeah, you're realizing that an AI is really only as smart as the semantic garbage you feed it.
It is the harsh reality of building real-world AI applications. The chat interface you see is pristine, but the ingestion pipeline beneath it, it's chaotic.
Highly chaotic.
If your pipeline parses a technical document incorrectly, or, say, slices a table in half, or loses the context of an architecture diagram entirely, your cutting-edge LLM is effectively blind.
Right. So today, we are taking your exact scenario, a small to medium IT organization with limited resources, and we're mapping out the entire life cycle of preparing complex technical documents for vector databases.
And since you provided us with your actual architectural diagrams and schemas, we're going to make this a highly visual deep dive.
Yeah, so throughout our conversation today, as we move from the broad database landscape all the way down to, the microscopic level of chunking tables and handling Git versioning, keep an eye on your screen.
We'll be walking through those exact mermaid diagrams you shared with us, step by step.
Seeing the data flow visually is really going to make the abstract math a lot more concrete.
Absolutely. So let's start with the foundation. Before you can even begin prepping your technical documents, you have to decide where they're going to live.
Right, the database itself.
Exactly. We need to look at the landscape of vector databases. And looking at your notes, you've been evaluating a pretty crowded field. Pinecone, Milvus, Qdrant, Weaviate, Chroma, and pgVector.
Yeah, and my first instinct looking at this list is to ask about the math. At the end of the day, aren't all of these databases essentially doing the exact same mathematical operation?
In a sense, yeah.
Like they take two high-dimensional arrays of numbers vectors and calculate the cosine similarity to find the closest match. If math is math, why should your team care if the database is written in Rust or Go or Python?
It's a really common trap to think the math is the product.
Yeah.
You are correct that calculating the cosine distance, measuring the angle between two vectors in 1536 dimensional space to determine how semantically similar they are, that's mathematically identical across all these platforms.
Right.
But the database isn't just a math calculator, it's an orchestration engine. The difference lies entirely in operations, memory management, and system architecture.
Okay, so how does that play out in practice?
Think about what happens when you aren't just comparing two vectors, but you're trying to find the closest match among, say, 5 million vectors, while simultaneously applying a filter that says only search documents tagged for the v2.4 API release.
Ah, okay, so the math doesn't help you filter, it only helps you compare.
Precisely. The math of cosine similarity is computationally expensive. You don't want to calculate it 5 million times if 4.9 million of those vectors belong to the wrong API version.
Yeah, that would be a massive waste of CPU.
Exactly. And this is where the underlying language and architecture of the database become critical. Let's look at Qdrant, which you noted is written in Rust.
Right.
My mind immediately goes to how Rust handles memory. Rust allows Qdrant to perform what's called single-pass filtering.
Single pass?
Yeah, it manages memory so tightly and predictably that it can apply those complex metadata tags like department or status while it's traversing the vector graph rather than filtering a massive list after the search.
Okay, that makes sense. It's not about the engine performing the calculation. It's about the transmission getting the data to the engine efficiently.
Exactly.
But what about Chroma? Because I see Chroma in almost every beginner AI tutorial on YouTube. And that one's written in Python, right?
Yeah, Chroma is brilliant for the lab. You can spin it up in 3 lines of code inside a Jupyter notebook. It is the undisputed king of rapid prototyping. But when you move to an enterprise production environment, Python's architecture becomes a bottleneck. Python has something called the Global Interpreter Lock, or the GIL.
Okay, let's pause on the GIL because that sounds like a massive roadblock. What is it actually locking?
In simple terms, the GIL is a mutex, a lock that protects access to Python objects, preventing multiple threads from executing Python bytecodes at once.
Meaning what for our server?
It means that even if you have a massive 64 core server, a single Python process can only execute one thread of Python code at a time.
Wait, really? Just one?
Yeah. Just one. For CPU-bound tasks like rapidly traversing massive arrays in RAM, you don't get true parallel processing.
Oh, wow.
This is why, when you run Chroma in its embedded mode, it tends to hit a performance wall around 20,000 to 50,000 vectors. The GIL basically becomes a traffic jam.
Okay, so Chroma is out for production IT department. That's a no-go. What about the other extreme? You've got Milvus, listed here, written in Go and C++, bam.
Milvus is the open-source heavyweight champion for sheer scale. It is built for extreme billion-vector datasets.
Billion?
Yeah, its architecture is incredibly sophisticated because it completely separates compute resources from storage resources. But this sophistication comes at a steep operational cost.
I can imagine.
Milvus requires a Kubernetes cluster to run properly. It relies on distributed components like Minio for object storage and Kafka or Pulsar for message brokering.
Yeah, so for a small IT team trying to build an internal tool, trying to deploy and maintain Milvus is like buying a commercial Boeing 747 just to commute to the grocery store.
That's a highly accurate assessment.
You're going to spend all your time doing maintenance and zero time actually flying.
Exactly. You'd need a dedicated DevOps engineer just to keep the infrastructure breathing.
Right. Okay, what about Weaviate? That one caught my eye because of the hybrid Jeff capabilities you highlighted in the source material.
Weaviate is written in Go and is arguably the winner for out-of-the-box developer experience. It has native machine learning modules, but its real superpower is that hybrid search you mentioned.
Which does what exactly?
It natively runs a BM25 search alongside the semantic vector search and then intelligently merges the results.
Okay, let me push back here to make sure we're totally clear. Semantic vector search understands the meaning of a phrase, but what exactly is BM25 doing under the hood that makes it so valuable alongside vectors?
Good question. BM25 is the industry standard algorithm for exact keyword search. It's based on a concept called TF-IDF, Term Frequency Inverse Document Frequency.
Right.
Semantic search is amazing at understanding that server crash and hardware failure are related concepts. But sometimes an engineer isn't looking for a concept.
They're looking for an exact string.
Yes, they are looking for a highly specific, obscure alphanumeric string, like error code 0x800 S081F. Semantic vectors can actually struggle with highly specific, rare tokens because the meaning of a random hex code is mathematically sparse.
It's just noise to the AI.
Exactly.
Yeah.
BM25, however, looks at the frequency of that exact string. Hybrid search gives you the best of both worlds: the conceptual understanding of vectors and the surgical precision of exact keyword matching.
That is genuinely powerful for a corporate knowledge base.
Yeah.
But looking at your final architectural diagrams, we aren't going with Weaviate, Milvus, Qdrant, or Pinecone, which as a managed sauce would lock us into their cloud ecosystem anyway.
Right.
We are targeting pgVector. Why turn a traditional relational PostgreSQL database into a vector store instead of using a purpose-built one?
Pragmatism, honestly. pgVector is an extension for PostgreSQL, and its adoption has skyrocketed because almost every IT department on Earth already has Postgres running somewhere. Your team already knows how to back it up, how to monitor its health, how to set up role-based access control. By using pgVector, you completely bypass the need to introduce an exotic, unfamiliar infrastructure stack, and it handles 10 to 50 million vectors with exceptional performance.
And there's a massive architectural advantage here too, right? If your vectors live inside Postgres, they live right next to your standard relational data.
Exactly. You could execute a single SQL query that joins your user permission table with your vector embeddings.
Oh, wow.
Yeah, you can write a query that essentially says, calculate the cosine similarity to find the most relevant architecture document, but interjoin it with the HR roles table, and only return the vector if the user making the query currently holds the senior engineer title.
That is incredible. Trying to synchronize complex, rapidly changing relational permissions with an external source vector database like Pinecone must be an absolute nightmare of network latency and race conditions.
That is, pgVector solves it by keeping the math and the relational logic in the exact same room.
So for your small IT team, the verdict is clear. Don't try to be a hero. Use pgVector. You get the stability, you get the relational joins, and you don't have to wake up at 3 a.m. because your message broker crashed.
Exactly.
So we have our vault, the database is selected. Now we have to talk about what we are actually putting inside it. How do we take a human-readable file and translate it into a machine-readable embedding?
This requires understanding what a vector truly represents.
Mm-hmm.
When we generate an embedding, we are taking a chunk of text and passing it through a neural network.
Right.
The output is a fixed-length array of numbers, typically 768 or 536 floating-point numbers, depending on the model. This array is a coordinate in high-dimensional space. But crucially, this array represents the pure semantic meaning of the text, completely stripped of its syntax, formatting, fonts, visual layout.
It's just a conceptual essence.
Yes. To the AI, the array 0.012 makes it 0.234.891 doesn't mean the word router. It points to the conceptual location of a router in relation to all other concepts it knows. But here's the challenge. Large language models and embedding models have strict context window limits. You cannot feed a 100-page manual into an embedding model and get one giant vector.
Because of the curse of dimensionality. Like if you compress an entire book into 1,536 numbers, the meaning becomes so diluted it's basically static, right?
That's a fantastic way to phrase it. It's like taking a bucket of red paint, a bucket of blue paint, and a bucket of yellow paint and mixing them all together.
Oh, you just get brown.
You don't get a beautiful rainbow, you get a muddy brown mess. If a document discusses network security on page 5 and cafeteria policies on page 95, a single vector trying to represent both will average out into a location in semantic space that means absolutely nothing.
Makes sense.
Therefore, we must split large documents into smaller, highly specific fragments called chunks. For technical documentation, the sweet spot is usually between 200 and 500 words per chunk.
Okay, so we have to chop our documents up. And this brings us to the format wars. Because how your original document is formatted completely dictates how successful this chunking process will be. And looking at your notes, PDF are essentially the villain of this story. Why is a PDF so uniquely terrible for AI to read?
Because a PDF is a visual illusion.
A visual illusion.
Yeah. When we look at a PDF on a screen, we see paragraphs, headers, columns, tables. But the underlying code of a PDF doesn't know what any of those things are. A PDF is simply a set of absolute coordinate instructions for a printer.
Like plotting points on a graph.
Exactly. The code just says, draw the letter T at x-coordinate 150 and y-coordinate 300 in size 12 Helvetica. Then it says, draw the letter H at x152. There is no HTML-style p tag wrapping them together to denote a paragraph.
So parsing a structured file, like Markdown, is like slicing a layered cake. You can look at the layers and know exactly where the chocolate ends and the vanilla begins. But parsing a PDF is like trying to unblend a strawberry smoothie to get the original individual strawberries back out.
The strawberry smoothie analogy is mechanically accurate. Because when you try to unblend that PDF using standard text extraction libraries like PyPDF, the parser uses heuristics. It usually just reads raw text left to right, top to bottom.
Which is fine for a novel, but
if your IT manual has a 2-column layout, the parser will read the first line of the left column, jump straight across the visual gap, and read the first line of the right column.
Oh.
Yeah, it physically glues two completely unrelated sentences together. Furthermore, it will seamlessly scrape page numbers, copyright footers, and floating image captions right into the middle of a critical code block.
Which means your LLM is suddenly trying to execute a script that has a copyright notice injected into the middle of a while loop.
Exactly. It generates semantic garbage. This is why, for technical documentation, Markdown is vastly superior. Markdown is natively structured and semantic. The author's intent is baked into the syntax. A single hash mark is definitively an H1 title. 2 hashes is definitively a subtitle.
So a parser doesn't have to guess based on visual coordinate.
Right. Tools like LangChain's Markdown headers text splitter build an abstract syntax tree of the document. They don't just blindly count to 500 words and chop the text like a meat cleaver. They look at the headers and split the document exactly where the author intended a new thought or new section to begin.
But whether the original file was a messy PDF or a perfectly formatted Markdown file, the database ultimately doesn't know the difference, right? What physically gets inserted into a row in pgVector?
The final output is standardized. For every single chunk, the database receives 3 distinct components. First, the vector array itself, the mathematical representation.
Right, the 1536 numbers.
Yes. Second, the payload, which is the raw, human-readable text of the chunk, because the LLM needs actual English words to read when it retrieves the result. And third, the metadata, a JSON object containing the context.
Stuff like source.apmanual.md section, authentication.
Yes. The database just stores the nutritional facts, the math, the text, and the label. Our job as engineers is to ensure the text we generate that vector from is as clean and context-rich as possible.
which is actually a massive hurdle. Even if you use Markdown and split the document beautifully at the headers, you still run into a severe problem with context loss.
You do.
Like, if a document is 50 pages long and chunk number 45 is just a paragraph that says press the start button to initiate the sequence, you've ripped that sentence completely out of its global context. The AI retrieves that chunk and has absolutely no idea what machine we are starting.
This is one of the most common failure points in retrieval augmented generation, or RA. The naive approach fails because of this context loss. To combat it, the architecture you provided uses advanced chunking strategies. The first technique is context enrichment, sometimes referred to as contextual inheritance.
How does that work in practice?
As your extract, transform, load pipeline, your ETL is reading down the Markdown abstract syntax tree, it keeps track of the hierarchy. When it prepares to finalize chunk 45, it programmatically grabs the parent headers and physically prepends them to the chunk's text payload.
So instead of the payload just being press the start button, the Python script edits the text to say context, router x10 Wi-Fi config, setup phase, press the start button to initiate the sequence.
Yes, and here's why that is so powerful. Because those contextual words are now physically part of the text string. They become part of the mathematical vector embedding.
Oh, I see.
The 1536-dimensional array shifts its location to explicitly include the concept of the router x10. When a user later asks the chat interface, how do I start the router x10? The semantic match is incredibly precise.
That's a brilliant way to force the LLM to remember the broader topic. You're basically stapling the chapter title to every single paragraph. What's the next strategy?
Parent-child chunking. This is arguably the most sophisticated architectural trick in modern RAG systems, and it leverages the fact that the chunk size that is best for searching is rarely the chunk size that is best for generating an answer.
Okay, unpack that for me. Why would those optimal sizes be different?
If you want highly accurate vector search, you want incredibly small, specific vectors. A vector representing just one or two sentences has a very dense, unmistakable meaning.
Right, less noise.
But if you only feed one or two sentences to an LLM as context, the LLM doesn't have enough background information to write a comprehensive, nuanced answer.
So we need small chunks for the search engine, but huge chunks for the LLM.
Yes. So we decouple them. You take a massive section of your document, say an entire page, and you store that raw text in your database. This is the parent. It gets a unique ID, but you don't generate a vector for it.
Okay.
Then your pipeline cuts that page into tiny one-sentence microchunks. These are the children. You generate vectors for the children.
Yeah.
But inside the metadata JSON of every child, you inject the ID of the parent.
Ah. It's like finding a book in a massive library. The child chunk is the index card in the catalog. The index card is highly specific, so you find it instantly. But you don't read the index card to learn the topic. The card just gives you the ID number to go pull the massive comprehensive book off the shelf.
That is exactly the workflow the user searches. The vector DB instantly flags the child chunk with a high cosine similarity score. But instead of sending that tiny sentence to the AI, your backend application runs a quick relational SQL query to fetch the parent ID, pulls the entire surrounding page of text, and feeds that into the LLM's context window.
That gives you surgical precision on the retrieval, but massive context on the generation. Combine that with dense tagging, where you inject heavy metadata like version numbers directly into the JSON to filter out irrelevant docs before the search even runs, and you have a robust text strategy.
Exactly.
But I see a glaring issue we need to address. This all sounds great for paragraphs, but IT manuals are full of tables. A Markdown table is literally just drawn using ASCII characters, right? It's pipes and dashes, like column A, column B.
Yes, and this is where standard chunking algorithms completely fall apart. If a text splitter hits a Markdown table and just slices it in half because it reached the 500-word limit, the structural integrity of the table is destroyed.
It's just mangled characters at that point.
But even worse, an embedding model passing text through a neural network struggles to understand the semantic two-dimensional relationship of a grid represented by vertical pipe characters. The vector representation of a Markdown table usually turns into semantic noise.
So how do we translate a visual grid into something an LLM natively understands?
We intercept the tables during the parsing phase, completely pulling them out of the standard text flow. In your architecture, you utilize the Python library Pandas. Pandas is an incredibly powerful data manipulation tool that can read Markdown tables natively. The pipeline extracts the raw Markdown table, loads it into a Pandas data frame, and then converts that data frame into a JSON array of records.
Why JSON? Is it just because it's a cleaner data structure?
It goes deeper than that. LLMs have been trained on billions of lines of code, APIs, configuration files. They have a profound native understanding of JSON structures. A JSON key-value pair explicitly semantically links the column header directly to the row value without relying on visual spacing.
Oh, I see.
So instead of a row that looks like timeout 31, Pandas transforms it into parameter name, timeout default value, 30.
The relationship is hard-coded into the text itself. The word timeout is explicitly bound to parameter name.
Exactly. And this introduces a critical architectural decision. Let's say you parse a massive 100-row table of API error codes into a JSON array. Do you take that entire massive JSON block and embed it as one single vector? Or do you iterate through the JSON array and create 100 separate vectors, one for each row?
My gut tells me you'd want them separate so you can find the exact error code faster. But does that break the context?
It's a tightrope walk. For small tables, say a 4-row summary of a hardware's text, you embed the entire JSON block as a single vector. The text is short enough that the vector retains the overall holistic context of the table.
But for the massive 100-row API error table?
For massive tables, you must use row-by-row vectorization. If you embed a 100-row table into one vector, the specific semantic signature of error code 404 will be completely drowned out by the noise of the other 99 codes. So you create 100 little vectors.
Okay, that makes sense.
However, and this is a trap that destroys many RA pipelines, if you isolate a single row to vectorization, the text string is just error, 404, meaning not found. That chunk has entirely lost the context of what system it belongs to.
Right. It could be an HTTP error, a custom gateway error, a database error. The LLM has no idea.
Precisely. Therefore, your Python parser must dynamically inject the table's overall title and context into the text or metadata of every single row before generating the vector.
So it stitches it back together.
Yes, the final string has to look like API Gateway Error Codes v2.0 error 404, meaning not found. Now, the LLM knows exactly where this tiny piece of data originated.
That is an incredibly elegant solution using Pandas to manually preserve the context that the visual grid used to provide. So we've optimized our text with parent-child links, and we've transformed our tables into JSON arrays. Now we need to actually push all of this perfectly formatted data into our pgVector database. But here is the reality of an IT department. This isn't a one-time upload.
No, documentation is a living organism.
Exactly. Your team's documentation lives in a Git repository like GitLab. It is being updated, tweaked, and rewritten constantly by dozens of engineers. Every time an engineer fixes a typo and hits commit, how do we keep the vector database perfectly synced with the Git repository without creating a catastrophic mess of duplicated chunks?
The absolute foundation of continuous synchronization is ensuring idempotency through deterministic IDs.
Idempotency, meaning no matter how many times you run the ingestion script, the final state of the database remains identical without creating duplicates.
Yes. The single biggest mistake junior AI developers make is using functions to generate random UUIDs for their chunks right before inserting them into the database.
Just assigning random strings.
Right. Think about what happens. You parse ap.md on Monday, generate random IDs, and insert them. On Tuesday, an engineer updates a single word in that file. Your pipeline processes the entire file again, generates brand new random IDs, and inserts them. The database now holds 2 copies of the document, slightly different. Run this for a month across a busy team, and your database is bloated with ghost duplicates. A user searches for a concept, and the AI retrieves the exact same paragraph repeated 5 times across different IDs.
So what's the mechanism to prevent that? If we can't use random UUIDs, how do we name these chunks?
You derive the ID from the unchangeable facts of the document itself. You create a cryptographic hash, like an MD5 or SHA-256 hash, based on a combination of the file path and the chunk's index number.
Okay, I follow.
For example, your Python script calculates the hash of the string docsampi.md chunk 0. That resulting hash becomes the permanent deterministic ID for that specific block of text.
So no matter how many times I run the pipeline on epi.md, chunk 0 will always generate the exact same hexadecimal ID string.
Exactly. And here is where we leverage PostgreSQL's relational power. When your pipeline sends the data to pgVector, you don't use a standard SQL insert command. You use an upsert, specifically the insert pandas pad. On conflict, id do update command.
Walk me through what that SQL query actually does when it hits the database engine.
The pipeline sends the chunk. Postgres looks at the ID and says, wait, I checked my index, and I already have a row with this deterministic ID. That is the conflict.
Right.
Instead of throwing an error or creating a duplicate, the update clause instructs Postgres to simply overwrite the existing vector, payload, and metadata with the newly provided data.
That's incredibly clean.
If the text hasn't changed, the overwrite is functionally invisible. If the engineer fixed a typo, the new vector gracefully replaces the old one. It is a self-healing process.
That is brilliant. But let's look at the compute efficiency. Even with UpSerts gracefully handling duplicates, we don't want our ingestion server grinding its CPU to a halt, re-embedding 10,000 files every single time someone pushes a small commit.
Which brings us to the Git Diff Pipeline. We don't process the entire repository on a commit. When a webhook fires from GitLab, the very first thing your backend does is execute a git diff namestatus command against the previous commit hash.
To see what changed.
Yes, this isolates the exact list of files that were added, modified, or deleted.
Added and deleted seems straightforward. For an added file, you run the chunking pipeline and upsert. For a deleted file, you extract the file path and run a SQL delete query where the ID begins with the hash of that path. But what about modified? If an engineer just adds one new paragraph to the middle of a document, do we just upsert the new chunks?
Modified is actually highly destructive to chunk boundaries.
How so?
Imagine a document with 10 chunks. An author adds a massive new paragraph at the very beginning of the file. The Markdown header splitter runs. What used to be chunk 4 is now pushed down and becomes chunk 5. The boundaries shift entirely.
Oh, I see.
If you just naively assert, the deterministic ID chunk 4 will be overridden with text that has a completely different semantic meaning, and chunk 5 will hold data that used to be in chunk 4.
You essentially scramble the entire semantic mapping of the document. So how do you handle a modification cleanly?
For a modified file, the safest and most mathematically sound approach is a wipe and replace. Your pipeline executes a SQL delete for all existing chunks associated with that specific file path. You clear the board, then you reparse, re-embed, and insert the file as if it were brand new. It ensures the chunk indices and their corresponding texts stay perfectly aligned.
This architecture is airtight for keeping the current state of the repo synced. But IT departments have legacy clients. Let's say the team releases version 3.0 of an API. The master branch updates, the diff pipeline fires, and the database updates. But you still have enterprise clients paying for version 2.0, and your internal support team needs to be able to search the old documentation to help them. If we just wiped and replaced version 2.0 with version 3.0, that knowledge is gone.
This is where we return to schema design. You don't just rely on the file path for your unique constraint. You expand your PostgreSQL schema to include a dedicated column for the Git branch or release tag, for instance, v2.0 or v3.0.
Okay.
Your primary key or unique constraint becomes a composite of the file path, the chunk index, and the Git tag.
So docsapia.mdchunk0v2.0 can live right next to docsapia.0v3.0 in the exact same database table without conflicting.
Exactly. Multiple versions coexist peacefully. When a support engineer uses the internal chat tool, the UI asks them, which version are you inquiring about? If they select version 2.0, your backend application simply appends a where git tag equal e2.0 clause to the SQL vector query. It instantly isolates the cosine similarity search to the legacy documentation subspace.
Okay, so we're pouring tens of thousands, maybe millions of these vectors into pgVector across all these different versions. To actually search this massive mathematical space instantly, I know pgVector uses an index algorithm called HNSW. You see this acronym everywhere in vector database documentation. Hierarchical Navigable Small World. It sounds deeply intimidating.
It is a complex algorithm, but it's the undisputed champion of vector search.
When I try to picture, I think of the 6 degrees of Kevin Bacon, but applied to data. Is it basically a system where you start with massive leaks across a network and then slowly zoom in on your target?
That is a phenomenal conceptual model. To truly appreciate why HNSW is necessary, we have to look at why traditional database indexes fail with vectors. Traditional relational databases use an index called a B-tree.
Right.
A B-tree is essentially a massive sorting game. It works flawlessly for one-dimensional data, like alphabetical strings or integers. When searching a B-tree, the database asks a binary question. Is the target bigger or smaller than the current node? And navigates left or right accordingly.
But a vector is a 1536-dimensional coordinate.
Exactly. In 1536-dimensional space, there is no bigger or smaller. There's only the distance between points in a hyperdimensional cloud. A B-tree breaks down completely because it cannot sort multidimensional space. This is referred to in data science as the curse of dimensionality.
Right.
If you don't have an index designed for it, the database has to perform a k-nearest neighbor, or KNN, search.
Which means checking the distance against every single vector in the entire database one by one.
Yes, a sequential scan. If you have 5 million vectors, calculating 5 million cosine distances for a single user query will lock up your CPU and take seconds or even minutes. HNSW bypasses this by constructing a graph. It takes inspiration from a classic data structure called a skip list.
How does the multi-layered aspect of it work?
Imagine a multi-story building. The top floor of this building is a very sparse graph. It only contains a tiny fraction of the total vectors, and they're connected by massive, long-distance links that span across the entire semantic space.
Okay, I'm picturing it.
When a search query enters the database, it starts on this top floor. It evaluates the nodes and makes huge leaps across the vector space to get roughly into the right conceptual neighborhood.
Like taking an express train that skips the local stops and only hits major cities.
Precisely. Once it can't get any closer on the top floor, it drops down a level. The graph on this next floor is denser. It makes smaller, more refined jumps. It continues dropping down through the layers until it reaches layer 0, the ground floor.
And what's on layer 0?
Layer 0 contains every single vector in the entire database, densely interconnected with its closest semantic neighbors. But because the algorithm took the express trains down through the layers, by the time it hits the ground floor, it is already right on top of the target coordinate. It only has to check a handful of local neighbors to find the absolute closest match.
So it turns a sequential scan of 5 million rows into a targeted drop that only checks maybe a few dozen nodes. That brings the search time down exponentially.
It brings search complexity down to logarithmic time. Searching 1 million vectors feels almost as fast as searching 10,000. It operates in milliseconds.
But there is no free lunch in computer science. What is the trade-off for this incredible speed?
We pay for it in RAM, and we pay for it in index build time. To make these lightning-fast leaps, the entire HNSW graph structure, all the nodes, the pointers, the layered edges, must reside in operational memory. It is RAM-heavy.
That makes sense.
Furthermore, inserting a new vector isn't as simple as just adding a row to a table. The database has to calculate where this new vector fits into the multi-story graph and draw all the new connecting links.
And in pgVector, you can tune how this graph is built using 2 main parameters, right? M and F construction. Let's break those down for the listener tuning their database.
M defines the maximum number of links or edges that any single node can have to other nodes in the graph. If you set hem higher, you get a much more densely connected graph. This improves search accuracy because there are more paths to travel, but it vastly increases the RAM consumption of the index.
And what about F construction?
F construction dictates the size of the dynamic list the algorithm uses to find the optimal neighbors while it is building the index. Essentially, how deeply does it search to find the perfect place to wire in a new node? So higher is better.
If you set F construction to a high number, say 256, your index will be perfectly optimized for search and recall accuracy. But your CI/CD pipeline will take noticeably longer to build the index every time a new commit is pushed. So for our small IT department that updates their documentation frequently throughout the day, they need to strike a pragmatic balance. You might choose a moderate F construction, so you aren't waiting an hour for the database to sync the HNSW graph after every minor typo fix.
Exactly. It's a delicate balance of build time latency versus search recall perfection.
All right, this brings us to a really fascinating and frankly gnarly part of the architecture you laid out, the visual nightmare. We've perfectly synced our text, we've handled the Git diffs, we've transformed tables into JSON arrays, and we're indexed beautifully with HNSW. But technical docs aren't just text and tables.
No, they certainly aren't.
What happens when our Markdown parser is cruising along and it hits an ImageLink.network architecture, schema.png, or an embedded.drawia file? Because as far as I understand, standard text models are totally blind to this.
They are completely blind. If you pass this string.network architecture, schema.png, to a standard text embedding model, it simply embeds the semantic meaning of a file path. It has absolutely zero concept that the referenced image contains a complex, critical network diagram showing a load balancer connecting to 3 application servers.
Right.
The entire visual context of the architecture is lost to the AI. Handling images and architecture diagrams is currently one of the hardest frontiers in R/drag engineering. Looking at the industry, we have 3 main approaches to solve this blindness.
Let's lay them out. Walk me through approach 1.
Approach 1 is the practical gold standard for teams that need control and security. We call it the dual loop ETL. When your parsing script is walking down the Markdown tree and it hits an image link, it pauses the standard text flow. It reaches out, grabs the actual image file from the repository, and sends it to a local vision language model, or VLM.
So we use a secondary specialized AI whose only job is to look at the picture for us.
Yes. You might run a model like Qwen2VL or Llama 3 Vision. You send the image to the VLM along with a highly specific system prompt. Act as an expert technical writer. Describe this architecture diagram in extreme detail. List all components, the direction of the arrows, the protocols used, and the relationships between the microservices.
That is fascinating. How does a VLM actually do that? Is it just guessing based on shapes?
VLMs use a specialized architecture. They have a vision encoder, often a vision transformer, or VIT, that chops the image into tiny patches and extracts visual features.
Okay.
These visual features are then projected into the exact same high-dimensional semantic space that the language model uses for text. So the LM can read the visual features as if they were words. The VLM processes the image and generates a comprehensive text description of the diagram.
And then what? We have this text description. Where does it go?
Your pipeline takes that generated paragraph and injects it directly back into the Markdown chunk, either replacing or supplementing the original image link.
Oh. So when the main text embedding model comes along later, it doesn't see a blind file path. It reads this beautiful, comprehensive paragraph describing the load balancer and the servers, and the resulting mathematical vector captures the actual architecture. That's incredibly smart. What's approach 2?
Approach 2 is the low-code, fully managed route. It involves using proprietary, cloud-based services like LlamaParse. Instead of running local models, you simply upload your complex document to their cloud API.
And they handle the rest.
Yeah, they have massive, highly optimized clusters of AI agents that visually scan the document. They are incredibly adept at recognizing complex flowcharts and will automatically translate them into mermaid.js code directly inside your text flow.
Wait, mermaid code, like the text-based architecture diagrams we're looking at on our screens right now?
Exactly. It converts a picture of a flowchart into the actual declarative code of a flowchart. It's a fantastic solution out of the box. But there's a fatal flaw for many IT organizations. It is proprietary and cloud-based.
I see where this is going.
You are sending your company's most sensitive internal network architecture diagrams to a third-party server. For many corporate security teams, that is an immediate NDA breach and a hard locker.
Yeah, your chief information security officer is going to have a heart attack if you start beaming the internal database schemas to an external startup. Okay, so approach 2 is out for our secure local IT team. What about approach 3? I was reading the source notes on this, and it honestly sounds like science fiction. It's a model called Colpoly.
Colpoly represents a paradigm shift. It is a late interaction architecture. With Colpoly, you completely abandon text parsing, you throw away the Markdown splitters, you don't convert tables to JSON, you don't run VLMs to write text descriptions of images.
Wait, what do you do then?
Instead, you take a literal, high-resolution screenshot of the entire document page.
You just take a picture of the page.
Yes. The Colpoly model then chops that visual screenshot into a grid of 32 by 32 pixel patches. It generates a multi-vector embedding based entirely on the visual layout, the font sizes, the bolding, the pictures, the arrows, the space between paragraphs, everything, exactly as a human eye processes a visual page.
Whoa, so it's not embedding characters or words, it's mathematically embedding the pixels.
Precisely. And when a user runs a search query, it performs a late interaction match across all those visual patches.
Yeah.
It is phenomenally accurate for highly visual documents because nothing is lost in translation.
So what does this all mean for our listener? Colpoly sounds revolutionary. It entirely skips all the headaches of parsing, chunking, and JSON tables we just spent 30 minutes discussing. Do we just throw out the old way and use Colpoly?
We have to reel it in and look at our specific constraints. Colpoly is revolutionary, but generating and storing dozens of visual multi-vectors for every single page requires an immense amount of video RAM on high-end GPUs. It also inflates the storage size of your vector database massively.
Right.
For a small IT team running a knee-high server in a closet or a modest AWS instance, the compute overhead of Colpoly is just too heavy right now.
It's the 747 problem again.
Yes. So we return to Approach 1. Approach 1 is the pragmatic gold standard for our scenario. It is highly secure, completely controllable, and hardware efficient. Your team writes a local Python script using a tool like Llama.
Let me jump in here because Llama is a great tool, but how are we running a massive vision model on a local standard IT server?
By using what's called a quantized model, neural network weights are usually stored as high-precision 32-bit floating-point decimals. That requires massive RAM. Quantization is a compression technique where we mathematically round those weights down to lower precision, like 8-bit or 4-bit integers.
Doesn't that hurt the performance?
You lose a tiny, almost imperceptible fraction of accuracy, but the model size shrinks drastically. Llama allows you to run these quantized VLMs locally on standard consumer-grade GPUs.
So you run a quantized VLM via Llama. It translates the internal images into text descriptions, stitches them back into the Markdown, and then you vectorize the text. All of your proprietary architecture data stays strictly inside your corporate firewall.
Exactly. It's secure and highly effective.
Okay, we have all the individual puzzle pieces. We've chosen pgVector, we have our chunking strategies, our Pandas JSON table extraction, our Git deterministic IDs, and our local VLM for images. It is time to assemble this machine. We are going to build the ultimate pipeline architecture for our listener.
Let's do it.
If you are listening, please direct your attention to the final mermaid architecture diagram on your screen. This represents the complete event-driven ingestion pipeline. We are going to walk through its 4 distinct layers. I'm looking at layer 1, events and sources.
This is the trigger layer. Everything is event-driven. An engineer writes a new section in an architecture document and commits it to the master branch in GitLab. This action fires a GitLab webhook. The webhook sends a tiny HTTP JSON payload to our server, simply stating, hey, a new commit happened. Our Git client component receives this, runs the Git Diff namestatus command we discussed earlier, and extracts exactly which Markdown files were added, modified, or deleted.
Clean and simple. Moving to layer 2, queues and dispatch. Looking at the diagram, I see a FastAPI receiver, a Redis instance, and Celery workers. Why do we need this entire queuing layer? Why not just have the Python script process the file immediately the second the webhook fires?
Because you have to design for the realities of human team dynamics. What happens on a Friday afternoon when 10 different developers all merge their code branches at the exact same time right before sprint deadline?
10 webhooks fire simultaneously.
Yes, and if your architecture processes them synchronously, your single server suddenly tries to boot up 10 heavy vision language models simultaneously to read images. The GPU completely runs out of VRAM, the out-of-memory killer steps in, and your entire server crashes. Layer 2 acts as a critical shock absorber. FastAPI is an incredibly fast, lightweight web framework. Its only job is to receive the webhook, say, got it, and instantly return a 200 OK status to GitLab so the webhook doesn't time out.
Smart.
Then, FastAPI packages that processing task and drops it into a Redis queue.
And Redis is just an in-memory data store acting as a waiting room.
Exactly. Then Celery, which is an asynchronous task orchestrator, manages the queue. Celery looks at your server resources and says, I only have enough GPU RAM to process 2 files at a time. So it lines the 10 tasks up and feeds them to the processing workers systematically, one by one. It keeps the server completely stable regardless of how many developers commit code simultaneously.
The shock absorber. I love that. Now we move down to layer 3, the ETL workers and the chunk context optimizer. This looks like the beating heart of the machine.
It is. A Celery worker picks up a file from the queue. It runs the Markdown AST parser to synchronously build a structural skeleton of the document. It maps out where the headers are, where the standard text is, and crucially, it identifies the heavy media, the tables, and the images.
And then what does it do with them?
And here is where the architecture gets highly sophisticated. It leaves placeholders in the skeleton for those heavy tasks. It routes the tables over to a dedicated Pandas worker. It routes the image links over to the Llama VLM client.
And then layer 4 is storage, using Hugging Face TEI for generating the vectors and our trusty pgVector for the database. But let's pause. I need to play devil's advocate and push back on layer 3 for a second.
Sure, go ahead.
The VLM might take 10 or 15 seconds to look at an architecture diagram and write a paragraph about it, but parsing standard Markdown text takes a fraction of a millisecond. Since Celery and Redis are fully asynchronous, these tasks are running in parallel. Won't the chunks get completely jumbled out of order?
What do you mean?
Like, if chunk 2 is waiting 15 seconds on an image, but chunk 3 is just text and finishes instantly, doesn't the document get completely scrambled when it hits the database?
That is the exact problem that breaks most asynchronous pipelines. And the solution is the chunk context optimizer, utilizing an architectural pattern called lazy assembly in Postgres. To understand how it works, we have to look back at the deterministic IDs we generated in our Git sync discussion, the MD5 hash of the file path and chunk index.
Right, hash, docsipy.md chunk 2.
The synchronous parser assigns those permanent IDs to the skeleton before it dispatches the heavy tasks to the asynchronous workers. So the order of execution fundamentally no longer matters because every single piece of data has a permanent cryptographic name tag.
Okay, I follow.
But to handle the actual assembly, we don't hold the data in Python's memory. Holding state in a Python worker is risky. If the worker crashes or restarts, you lose the document. Instead, we push the assembly logic into the database. We create a temporary table in PostgreSQL called raw chunks.
Wait, relying on Postgres to handle application logic, using the database as a holding pen. Isn't that considered an anti-pattern by modern backend developers? Why push that into the database layer instead of handling the state in Celery?
It's a great challenge. While it is generally an anti-pattern to put complex business logic in a database and highly concurrent asynchronous data pipelines, using the database as a state machine is actually incredibly robust.
Really?
Yeah, Postgres is fundamentally designed to handle concurrent writes and guarantee ACID compliance, atomicity, consistency, isolation, durability far better than an ephemeral Celery worker.
Okay, so how does this raw chunks table actually work as a state machine?
The table is designed with columns for the chunk kid, the base text, the table JSON, and the VM description. When the initial parser runs, it creates a row for every chunk. If chunk 3 is just text, it fills the base text column and its status is marked ready.
Right.
But chunk 2, which contains an image, gets its base text filled, but its VM description column remains NLL. Its status is pending.
So it's literally just sitting in the database waiting for its missing piece.
Exactly. 10 seconds later, when the Llama VLM finally finishes describing the image, the Python worker executes a simple update statement on the raw chunks table. Update the row where the ID is chunk 2 and set the VLM description to this new text.
And how does it know when everything is done?
Inside PostgreSQL, we write a database trigger. A trigger is a function that runs automatically on a specific event. As soon as the update happens, the trigger checks the row. If the row has no more NLL values, meaning all the asynchronous Pandas and Llama workers have reported back the trigger fires,
Oh, wow.
it concatenates the text, the JSON tables, and the VLM image descriptions together into one perfect string.
Then it takes that perfect string and sends it to the embedding engine.
Yes, it sends it to Hugging Face TEI.
Why Hugging Face TEI specifically? Why not just use a standard Python script to run the embedding model?
TEI stands for Text Embeddings Inference. It's a dedicated Rust-based server specifically optimized for generating embeddings at massive scale. It handles dynamic batching, grouping multiple text chunks together to process on the GPU simultaneously, and manages memory far more efficiently than a native Python script.
That makes sense.
TI generates the 1536-dimensional vector, returns it to Postgres, and finally, the pipeline executes that upsert command to move the finished product from the raw chunks holding pen into the main pgVector HNSW index. It is an entirely self-assembling puzzle.
A self-assembling puzzle guaranteed by the mathematical reliability of a relational database. The Redis queue prevents the server from clashing under load. The deterministic IDs prevent ghost duplicates. The quantized local VLM cures the AI's blindness to diagrams securely, and the lazy assembly in Postgres solves the asynchronous chaos.
And critically, all of this runs entirely within the perimeter of your small IT department, using open source tools, keeping your proprietary data completely secure.
Wow, okay, what a journey. From the abstract math of vector space down to the nitty-gritty of Postgres triggers. If you are listening, you now have the exact blueprint to build this. You know why we are skipping the massive Kubernetes clusters of Milvus and choosing pgVector for its stability and relational joins.
Yeah.
You know how to tear your documents down, smartly ditching the visual illusion of PDFs for the semantic structure of Markdown. You understand how to enrich those chunks with parent-child inheritance so you never lose context, and how to use Pandas to translate complex visual tables into LLM-friendly JSON arrays.
And you understand the mechanics of keeping your database perfectly synced with your GitLab repository, using cryptographic MD5 hashing for idempotency, ensuring your lightning-fast HNSW index remains pristine.
Right.
You have a strategy for curing your AI's visual blindness by routing architecture diagrams through local quantized vision language models. And you know how to orchestrate that entire symphony with a robust, event-driven pipeline that leverages the database itself to gracefully assemble the asynchronous chaos.
It is an incredible architecture. But, as we wrap up this deep dive, I can't stop thinking about our brief detour into Colpoly. Those 32 by 32 pixel patches. It leaves me with a somewhat provocative thought about the future.
Oh, yeah.
Right now, we are spending massive engineering effort translating visual intent into machine-readable syntax. We are writing scripts to turn tables into JSON and using VLMs to write paragraphs describing flowcharts. But as multimodal models like Colpoly become computationally cheaper and hardware inevitably patches up, we are moving from analyzing text to analyzing pure pixels.
It is the ultimate trajectory of the technology. The history of computing is the history of removing abstraction layers between human intent and machine understanding.
Exactly. If an AI can just look at a screen exactly the way a human eye does, intuitively understanding the layout, the color coding, the spatial relationship of a diagram, will the concept of a document format simply cease to exist?
It's entirely possible.
Yeah. If the AI is just reading the visual rendering, it doesn't care if it's a PDF, a Markdown file, or a Word document. Are we entering a post-format era of data engineering where the intricate parsing pipelines we just spent an hour building become entirely obsolete?
It is a profound question. When the machine no longer needs the syntax to understand the intent, the entire paradigm of data engineering shifts from parsing structure to managing visual fidelity.
Something for you to mull over as you deploy your pgVector database and configure your webhooks this week. And on that note, we'll sign off. Your deep dive is complete. You've got the diagrams, you know where the traps are hidden, and you are now ready to build your own enterprise-grade, chaos-proof vector pipeline. Thanks for joining us. We'll see you next time. And remember, AI might feel like magic, but now you know exactly how to build the plumbing.